The Sea Venom, sometimes known as ANL Air-to-Naval Light, an earlier program references and internationally marketed as Sea Venom ANL, is a modern precision anti-ship missile developed to give rotary and fixed-wing aircraft a compact, accurate, and low-collateral option for engaging hostile surface vessels. It's the result of a cooperative Anglo-French effort between MBDA, with roots in both countries' defense industries, and reflects a clear contemporary design philosophy: small footprint, high accuracy, flexible guidance, and minimized risk to non-combatants and infrastructure. In this video we'll take a close, plain English look at the Sea Venom's exterior profile, the important internal subsystems, what you can reasonably call its interior, its performance envelope, launch and integration options, and the practical price and procurement picture, all explained for enthusiasts and professionals who want a thorough but non-technical understanding. Visually, the Sea Venom is compact and purpose-built. It's noticeably smaller than heavy anti-ship missiles like the Harpoon or Exocet, reflecting its role as a light, anti-surface weapon rather than a heavyweight strike munition. The missile's length and diameter are optimized so it can be carried on helicopters, for example, on platforms such as the Royal Navy's Wildcat and the French Navy's Tiger, and on fixed-wing aircraft where appropriate. The external skin is smooth and streamlined to reduce drag during launch and to help preserve seeker sensitivity in the terminal phase. You'll see small control fins and actuators along the body. These are sized to provide the maneuverability needed for attack profiles while keeping the missile compact enough to fit under a variety of pylons and in some internal bays. The nose is dominated by the seeker dome, which is a key visual cue to the missile's capability. Sea Venom employs an imaging infrared (IIR) seeker for terminal guidance, enabling high-resolution target discrimination in the final seconds before impact. The dome is typically made of a material optimized to transmit infrared wavelengths while protecting the seeker from thermal and mechanical stress. Behind the seeker, the missile shoulder and midsections carry avionics bays and the warhead compartment, usually encapsulated to simplify handling and carriage. The aft section hosts the propulsion unit and the control surfaces that stabilize and direct the weapon in flight. The exterior also features discrete mounting points and electrical data connectors that allow aircraft to interface with the missile for mission planning and target cueing. Opening the black box metaphorically, the interior of the Sea Venom is a layered system of sensors, processors, control mechanisms, and the warhead, each optimized to balance capability, reliability, and maintainability. The seeker itself is an imaging sensor with onboard processing. Instead of a simple heat point tracker, it builds a thermal image and runs pattern recognition routines to identify candidate targets. That imaging capability gives it stronger resistance to decoys and clutter, and it enables the missile to discriminate between different types of vessels or to aim for specific parts of a ship such as the superstructure or the waterline. The guidance architecture is typically multi-mode. Before launch, the weapon can be cued by the launch aircraft's sensors, radar, electro-optical infrared pods, or data link targeting information from other platforms like maritime patrol aircraft or drones. During mid-course, a navigation package, usually an inertial measurement unit coupled with GPS, keeps the missile on a computed intercept route. As it approaches the target area, the IIR seeker takes over for terminal homing. That layered approach lets the Sea Venom balance long-range navigation with precision endgame targeting, and permits flexible missions such as seek and strike against moving small and medium-sized vessels. Internally, the electronics and power systems are compact and robust. Power is normally provided by a reserve battery that activates on launch. These are engineered to survive long storage, temperature swings, and vibration. The flight computer runs guidance laws and signal processing software that fuse inertial GPS data with seeker returns. Importantly, modern Sea Venom software includes target queuing and target prioritization logic that lets the missile select from several nearby signatures, minimizing the risk of striking non-combatants or misidentifying benign craft. Redundancy and fault-tolerant design are built in so that single-point failures are unlikely to lead to catastrophic behavior. The warhead is a carefully matched compromise of weight, blast fragmentation design, and fusing. Sea Venom's effect is optimized for disabling small to medium surface vessels, hull breach, critical system damage, and mission kill rather than simply overkill. That means a warhead engineered to maximize effect against maritime targets while limiting high-order blast to protect nearby shipping or structures when operations are conducted in congested littoral waters. The fuse takes cues from the seeker and may employ proximity and impact elements to ensure detonation at the right standoff and angle. Propulsion is typically a solid rocket motor sized to the missile's lightweight roll. The motor provides the boost and cruise energy needed to close on the target at a relatively low altitude or sea-skimming profile. The flight profile is designed to reduce exposure to shipboard air defenses, a low approach, pop-up maneuver for terminal acquisition, and then a high-angle or sea-skimming terminal run depending on mission planning and the target's defenses. Control surfaces and actuators allow the missile to maintain high maneuverability, which matters when engaging fast attack craft or in cluttered littoral environments. From an operational standpoint, Sea Venom is intended to be launched from helicopters and small naval aircraft but can be adapted for other platforms. Helicopter launch provides distinct advantages. The platform can operate at altitude, stand off and use its sensors to cue the missile, and helicopters can loiter to prosecute fleeting contacts. When integrated on fast jets, the missile benefits from speed and range. Integration includes not just physical mounting but data and mission planning coupling. The aircraft must be able to pass target coordinates, seeker modes, and engagement parameters to the weapon. For modern navies, Sea Venom offers a flexible option to arm smaller ships or helicopters with precision standoff strike capability without the infrastructure or cost of heavier anti-ship missiles. Performance metrics are best thought of as fit for role, rather than absolute extremes. Sea Venom is not designed to replace heavyweight anti-ship missiles that punch through major warships' armor and layered defenses. Instead, it excels against fast attack craft, patrol boats, logistic ships, landing craft, and other small to medium maritime threats. Typical engagement ranges, which vary by launcher, flight profile, and avionics integration, place Sea Venom in the tactical standoff band, enough range to keep the launching platform outside short-range defensive envelopes, but short enough to permit precision engagement. Speeds are subsonic to transonic, fast enough to challenge targets and minimize reaction time but again deliberately matched to its lightweight, precision-oriented mission. One of Sea Venom's real advantages is its terminal accuracy, driven by the IIR seeker. That precision reduces the need for large warheads and lowers the risk of collateral damage when operating near civilian shipping or in port areas. Another practical performance benefit is all-weather functionality. While infrared seekers are usually sensitive to weather, modern imaging seekers combined with pre-launch queuing and mid-course updates allow effective employment in many conditions. That said, like all sensors, performance will degrade in extremely adverse conditions such as heavy rain or dense smoke. Mission planning accounts for these limitations. Operational history and testing show Sea Venom performing well in trials, demonstrating effective lock-on to hit sequences against representative naval targets and showing the ability to be integrated across multiple airframes. Beyond pure lethality, testing focuses on safe carriage, separation dynamics, the way the missile cleanly departs a helicopter or aircraft, and seeker performance in cluttered maritime littoral environments. Those integration trials are crucial because a missile's performance in an ideal test range often differs from the messy real-world environment of sea clutter, multiple targets, and electronic countermeasures. On the electronic countermeasures front, Sea Venom's design philosophy emphasizes sensor fusion and onboard processing to reduce susceptibility. Because the seeker images the target rather than merely homing on a heat point, it is better able to ignore decoys like flares or misleading thermal signatures. Additionally, mid-course updates and target queuing reduce the need for seeker-only acquisition in complex scenarios, allowing human-in-the-loop correction where necessary. That said, in contested environments with sophisticated shipboard countermeasures, tactics such as coordinated sensor feeds, multiple launch angles, and saturation employment remain part of doctrinal responses. This missile is a tool in a broader tactics toolbox, not a silver bullet. Cost and procurement are often the decisive factors for modern navies and air arms. Sea Venom is positioned as a cost-effective precision weapon that allows smaller platforms to carry out missions previously requiring larger missiles or more expensive sorties. Exact unit cost depends on buyer configuration, production lot, integration work, training, and spare parts. Defense procurement rarely buys single items in isolation. Ballpark public figures from various light anti-ship missile programs suggest that modern precision lightweight missiles are priced to be significantly less than heavyweight anti-ship systems, often in a bracket where widespread procurement is budget feasible for a wide range of operators. The economic case hinges on the missile's life cycle costs, storage, shelf life especially for batteries and propellant maintenance cycles, and upgrade pathways for its seeker and software. From a logistics standpoint, Sea Venom aims to be relatively low burden. Its compact size simplifies storage aboard ships and reduces handling infrastructure needs. Software-based upgrades to seeker logic and target libraries can extend the missile's relevance without wholesale hardware replacement, a major advantage in terms of long-term procurement cost and capability refresh cycles. Training and integration costs, meanwhile, represent the upfront investment. Crews must learn to plan engagements, queue seekers, and understand the missile's limitations as well as its strengths. Export and strategic use raise additional considerations. As a precision weapon intended for littoral and regional conflicts, Sea Venom is attractive to nations that require flexible, lower collateral options for maritime security, interdiction, and asymmetric defense. Its smaller warhead and precision means it's also politically more acceptable for operations in congested sea lanes or near civilian traffic, which increases its utility for coast guards and navies conducting counter-piracy, interdiction, or embargo enforcement missions. Conversely, major surface combatants will still retain heavier anti-ship missiles for shore bombardment and anti-capital ship missions. There are also important safety and legal considerations. Modern weapons like Sea Venom are designed with safety interlocks, arming delays, and secure handling procedures to prevent accidental detonation or unauthorized use. Export controls, end-user agreements, and international law govern transfers and employment, factors that influence market dynamics and strategic availability. Looking forward, the Sea Venom family and similar lightweight anti-ship missiles will likely evolve in predictable ways. Longer range through improved propulsion or carriage options, more sophisticated seeker fusion, for example combining IIR with millimeter wave radar for adverse weather performance, and tighter integration into networked maritime battle management systems. Autonomous teaming concepts, where unmanned surface vessels or drones work with manned aircraft to identify and prosecute targets, could make weapons like Sea Venom even more effective, enabling distributed engagement from multiple vectors. In practical terms for pilots and mission planners, Sea Venom represents a flexible and modern answer to a changing maritime threat environment. It gives helicopter squadrons and smaller air arms the ability to field precision, standoff lethality without needing heavy missiles designed for blue water fleet engagements. That changes force posture. Coastal and littoral defense becomes more distributed, cheaper to field, and less dependent on large platforms. In summary, Sea Venom is a thoughtfully engineered light anti-ship missile, compact externally, sophisticated internally, and designed to deliver precision effects in the complex littoral battlespace. Its imaging seeker, layered guidance approach, and tailored warhead create a weapon optimized not for brute force but for accurate mission kills with minimized collateral damage. The missile's procurement economics and integration flexibility make it a practical tool for modern navies and air forces seeking to balance capability, cost, and political constraints. As maritime security challenges continue to evolve, systems like Sea Venom will remain central to how nations project precision power at sea while managing the strategic and ethical complexities of modern conflict.